we'll discuss charge lattice. We'll try to argue that both magnetic and charges and electric charges should live on a lattice. Recall we had Dirac, Saha, Schwinger, Zwan-Ziegler quantization condition for dions with charges, electric charge Qi, magnetic charge Gi, set of dions, and we had argued that they satisfy a relation Qi Gj, or let me say 1, 2, Q2 G1 is 2 pi some integer n12 cross H cross. And this integer n12 is if this n12 is an integer plus minus 1 plus minus 2. And then we had recognized that this object has an invariance under duality rotation, that is Qi plus I Gi, this combination, if I rotate it by a phase multiplied by phase I phi Qi plus I Gi, then this relation is invariant. And I hope that was an exercise that you check. In fact, we also made a remark there is a larger invariance of this relation, which is SL to R, wherein Gi, Qi go to R, S, T, U, Gi, Qi, where R, this 2 cross 2 matrix Ru is a unit determinant matrix. RUST. But now today we'll argue that the values of Q plus Ig, the electric charge plus I times the magnetic charge for localized states like dions lie on a lattice. That is, the invariance of this relation holds for a discrete group, not a continuous group like SL2R or a phase like this, but a discrete group which is SL2Z, where Z is set of integers. So that is that this transformation Gi Qi goes to N L M K times Gi Qi, where determinant of these sets Nk times Lm is 1 and N, K, L, M all are set of integers, or take values in set of integers. So we'll argue that quantum mechanics semi-classical arguments tell us that the real invariance is smaller than this SL2R. It's only a discrete group which is SL2Z. And to do that, we'll make few assumptions. To demonstrate this, yes, but that is this relation. But then we'll explore other properties of this system and realize that though this relation is invariant under this, the real properties of electric and magnetic charges, quantum properties of electric and magnetic charges are such that they realize only invariance under SL2Z, which is a discrete group. And to do that, we'll make the following assumptions. So to do so, we'll make use of the following facts. One, that there are purely electric charge of particles. There are purely electrically charged states. That means they have no magnetic charge. But that's not really an assumption, because electron is a purely electrical charge object. So this is not an assumption, this is a fact of life, not an assumption. Two, we assume that there is at least one purely magnetically charged state, that is magnetic monopole. That we have not seen in nature. So this is an assumption. We have not seen it as yet. And then conservation of charge. That is, any sum of physical charges or is also a physical charge. Which if I have two states with charge Q1 and Q2, then Q plus Q2 is also a possible value for charge. Four, we'll assume CPT theorem. That says that if Qg is an allowed set of values for charge, then minus Q and minus G is also a physical value of charges. That simple statement that if I have a state Q with charge Q and G, then I also have an antiparticle state with charge minus Q and minus G. So this is antiparticle state. Then fifth, we'll use this Dirac, Saha, Schwenger, Zwanzier semi-classical quantization condition. And that is for dions with charge Qi and Gi. We wrote it there, we'll write it again. Qi Gj minus Qj Gi is 2 pi Nij H cross for Nij's a set of values. Nij takes values in set of integers. So now let's build up an argument using these assumptions why this is the invariance that the charges must, values of charges must satisfy.
V is electric charge.
Yes.
Or
It's both in fact. Now let's start with building up the argument for this. Consider a set of particles with only electric charges. Which means some electric charge is Qi and they have no magnetic charge. And then we know that as long as there is a magnetic monopole of charge 0 G, pure monopole, no electric charge. This condition or Dirac-Saha condition tells us that Qi times G should be 2 pi H cross some integer Ni. And now let me rewrite this as, from here as Qi is 2 pi H cross divided by G Ni. And call this object some Q0 prime. And remember, Ni takes values in the set of integers. And this is the statement that we made earlier. What this tells us that electric charge is quantized. Pure electric charge is quantized, and it lives on a one-dimensional discrete lattice. Let E0 be the minimum positive value of electric charge. Now this Q0 that we have primed, that we've introduced, would be related to E0. Either it could be E0 or would be an integer times E0. So this E0 could be Q0 prime or an integer times Q0 prime. So that this relation is valid.
Q0 prime should be an integer times E0.
But if I put an E0 here, that E0 would also be an integer times. If I write this as minimum charge, then that would be some integer times E0. So then the Q0 should be,
Q0 should be an integer times E0.
well, is the other way around.
No, no, it's
It's just
prime 0 or it's twice Q prime 0 or twice
Then that would mean Q0 prime is set times E0 is twice Q prime.
Yeah.
E0 is the minimum.
That really, maybe you don't have charges of 1, you might have charges of twice.
I think it's all right. Maybe we'll work it out. All right. Well, if then E0 is the smallest charge, then smallest magnetic charge, let me call it G0, would be E0 times G0 is 2 pi h cross times some N0. That tells me G0 is 2 pi h cross E0 times N0. And this N0 would be a property of the theory, because you remember for Georgi-Glashow model, we saw that E0 and G0, the lowest charge in the for the purely electric objects, and the lowest charge, that is purely magnetic monopole, they were related by this kind of a relation with Georgi-Glashow model with N0 equal to 2. Then charge of an arbitrary magnetic monopole would be, G would be m times G0. This is the minimum value. M. For example, again in Georgiev-Glashow model we have an anti-monopole for which M is -1. So Gi, Mi, let me call it Mi. So that's one fact. Next, now let us consider a set of dions with charges Q1 and this minimum value G0 and Q2 and this minimum value G0. For such states from this relation, what do we have? We have Q1 minus Q2 times G0 is equal to 2 pi h cross n1 2. Which I could rewrite as Q1 minus Q2 is 2 pi h cross G0 n1 2.
Why do you call this the smallest magnetic charge? E naught is small, right?
E naught is smallest electric charge.
Yeah. And it
No.
comes as 1 by E naught, right? So if
Yes.
you have larger and larger values of E, then I think smaller and smaller values of G naught.
Yes, but for some smallest value of E, there is some E naught, there is some value for G naught.
That's right, yeah.
Right?
So it is a magnetic charge corresponding to the smallest E. Need not be the smallest magnetic charge.
No, that would also be the smallest magnetic charge.
No. And I can make the charges like 200 times E. And G naught is 200 times smaller. Because the product is always 2 pi L.
Yes.
So if one is big, the other is small. So,
We'll see. I think we'll see that argument. That's precisely what the lattice will emerge.
oh, I see.
Now, I can rewrite this object like this, and now E naught, G naught is this time this object. So I can rewrite this as E naught, n12 divided by n0 times E naught. And call this object n12 by n0 to be k E0. Now this k is an integer divided by an integer, some number. But then we said that sum of physical charges is also a physical charge. So if these two objects are physical charges, then Q1 minus Q2 magnetic charge 0 is also a physical charge. Is also a physical charge. But this is a purely electrical charge. And if it's purely electrical charge, then it has to be an integer multiple of E naught. K is an integer. So this tells me that values of n1, 2 and n0 have to be such that their fraction is also an integer. Now, if this be true, this relation is true, and k is an integer, then that tells me I can write Q1 and Q2 for the dions, this set of dions, in the following way. That implies Q1 can be written as some E naught times N1 plus an arbitrary factor which I will call theta by 2 pi, and Q2 would be E naught N2 plus an arbitrary factor, the same arbitrary factor theta by 2 pi. Because that's a possible solution to this equation. I take the difference of these two objects, this term can cancel away, I'll get E naught N1 minus N2, and that is what is k. But now I have introduced an object, an arbitrary thing. It is not an integer. There is no constraint on it. Only thing is I have normalized it by 2 pi by for some convenience. So to repeat it such that Q1 minus Q2 is simply E0 times N1 minus N2, and that what we had learned from here is E0k, and that we learned is also N1 by 2 E0 by N0, and that is also what we learned from 2 pi h cross N12 by G0. And in these relations, k, N12, N1, N2 are all integers. But not theta. So that's one set of argument. Now let me go and consider a different situation. Consider set of charges Q1 and m times the minimum possible magnetic charge G0, and Q2 times minimum the same charge. There we considered with 1 unit of G naught. Now let's consider with an arbitrary m units of G naught as the magnetic charge. Then Q1 minus Q2 would be 2 pi h cross N1 N2 divided by m times G0. Just use this relation. M times G0, take it common, take it on this side. That's what it is. N12 is for set of 1 and 2 given in by the theory, whatever theory you have.
We use the same symbol there.
Right. For this set and for that set, N12 is the same. Because that's this general relation. Yes, yeah, this N12 could be different. Some number. Now this I can rewrite as N12, but G0 I know how to write in terms of E0. So that would be M times E0, and this I will call P times E0. Now the same argument tells me that P has to be integer. So that tells me that all N12 M P are integers. It's a repeat of that argument, except that I have not I have taken the common magnetic charge for two sets of dions to be M units of the minimum charge.
It should be like not also.
And not, I missed somewhere and not here. No, I think I got it. E0 is here and N0 is here. Yeah.
No, what we have done was right.
No. E0 must be in the numerator.
I know.
And this is, I think, this is, I wrote it wrong. Right? So that this combination, N1, 2, P, N0, all of these are integers. But so it must be P. So like I did it there, this tells me that Qi for this set of theories can be written as E0 Ni plus an arbitrary object, I'll call it theta by 2 pi and some Fm. What I have done is I have generalized this to objects which have common charge m times G0. So the way I argue that this must be the solution, except that I have parameterized that arbitrariness here as theta by 2 pi times Fm, where Fm could depend upon the value m. And that was a situation when m was 1. So F1 was 1. In general, it could depend on m. See, this is F subscript m, not m. In general, it could depend on m because that still solves this equation. Pure electric charge. And here N1 minus N2 would be P. So that's, here I generalize that. Now, next let me consider a set of dions with charge Q1 and 1 unit of magnetic charge G0, or m units of magnetic charge and Q2 with 1 unit of magnetic charge. Clear? And let me rerun the same argument for such a situation. Put it in the quantization condition here. What do I have? I have Q1 times G0 minus m times G0 Q2 is equal to 2 pi n1 to h cross. That tells me Q1 minus mQ2 is equal to 2 pi n1 to h cross divided by G0. Now, if I try to solve this, what do I have? I can write Q1 as E0 N1 plus theta by 2 pi Fm. Q2 is E0 N1 plus theta by 2 pi F1. This is m units of charge, so Fm magnetic charge, this is 1 unit of this, sorry, this is N2, that's what you. Now, if I use that and then calculate this object, which is G0 Q1 minus m times Q2, from here I have E0 G0 N1 minus m times N2 plus theta by 2 pi Fm minus theta by 2 pi F1 m times. Substitute in this. That is E0 G0 N1 minus m N2 plus take theta by 2 pi common Fm minus m F1 . But that object is equal to 2 pi N1 to h cross. This quantity is 2 pi h cross times N0. What this tells me is that this, since this is an integer, it tells me that N0 times this combination must be an integer, right? This tells me N12 is N0 times N1 minus m N2 plus theta by 2 pi Fm minus m times F1. Is that clear? N12 is an integer, N0 is an integer, these are integers, this is not. So the only way I can satisfy this is theta dependence must disappear. Clear? This is F sub m. And since F1 is 1, we argued from there. This gives us the final result. This gives us the final result, and that is for a dion with charge Q times m naught, I have m times g naught, because that's what we had here. Here, Q1, right? So I'll just call it Q now. Q is E0 times n plus theta times m by 2 pi. And if I write Q plus I G, that is E0 n plus theta m by 2 pi plus I m G0 for this dion. This is the Q, and G, this is G is this. So let me rewrite this as now E0 n plus m theta by 2 pi plus I G0 by E0 take the E0 out, write this, and write this combination together. But what is G0 by E0? G0 times E0 is 2 pi h cross n0. So write G to be 2 pi h cross n0 by E0 square. Rewrite this as E0 n plus m times tau, where tau is a complex quantity which is theta by 2 pi plus I 2 pi h cross n0 divided by E0 square. Remember again, for Georgi-Glashow model, n0 is 2. So n0 is a model dependent quantity. It depends on what model you are studying these states in. And then what it tells us is that the charges, electric charges and magnetic charges in such a theory would lie on a lattice with period E0, two-dimensional, and a period E times tau. a complex period. So let me write it in words. Conclusion. Charges of a dion must lie on a two-dimensional lattice with periods E0 and a complex period E0 times tau, where tau is some arbitrary parameter theta by 2 pi plus I 2 pi h cross E0 by N0. Something we did wrong. N0 upstairs and E0 square downstairs, right? So now if the charges have to lie on this kind of a lattice, then this lattice, this set of charges is not invariant under the continuous transformation that we talked about in the beginning. So this argument tells us that the charges, which is Q plus I G as E0 times N plus M tau, do not satisfy the continuous invariance of the original quantization condition, but only discrete invariance. And you can check it and the discrete that it is SL2O. An important property, note this, imaginary tau, just calculate the imaginary value of tau here. What is it? It is 2 pi h n0 by E0. E0 was the smallest positive electric charge. N0 was the smallest positive number characterizing a theory. So this is positive. So which means this tau, the complex object tau, is only on the upper half plane. Something is E0, right? Square. I forgot the square. Yeah, in fact, E0 square is anyway positive. E0 square is important.
If you take M times E0 tau, then E0 tau will have E0.
No, that can be negative because M can be negative. But
If you define E0 tau as the combination, instead of putting the tau E0 outside.
no, E0, the tau as defined by this.
M is the integer, right? So M times E0 tau is what you have.
Yes, but this tau has the property that it's positive. So this tau parameter that you have lives only in the upper half plane. And upper half plane is invariant under SL2Z transformations. And that I leave as an exercise, but first thing I want to make an observation is this quantity is something familiar. 2 pi h cross by E square multiplying n0. This is essentially the inverse of, up to this n factor of infer 4 it should have been, is an inverse of the electromagnetic coupling. Electromagnetic coupling is up to some small factors, element is E0 square by 4 pi h cross. Now what I want to do is that we have an understanding, we have introduced 3 objects in our basic structure, E0, G0 and theta. E0 we understand because E0 is the smallest positive charge, G0 is the smallest magnetic charge, but theta is something that we have no understanding. Theta is an arbitrary object here. Clear? We have introduced an arbitrary object theta here. So let me try to understand what this theta is. So let me write again. E0 is the smallest positive charge, G0 is smallest magnetic charge, and N0 is a quantity, depends on the model, it's a given, depends on the model. For a model is an N0 is given fact to us. But what is theta? In developing an understanding of theta, we'll understand what is known in the literature as Witten effect. Which means Witten effect gives us an understanding of theta parameter that we have introduced here. In quantum gauge theories, non-abelian gauge theories, there is a parameter. We'll give that parameter also a name theta, and then we'll argue that that theta is the same as this theta. Theta called instanton number. Or instanton parameter. One thing to realize is that in a Yang-Mills theory, that is non-abelian gauge theory, we can always introduce an additional term in the Lagrangian density, and let us give it a name, L theta, and let me get the coefficients right. Theta by E square by 32 pi square, that's just some convenient normalization, times F mu nu A, F A mu nu dual, where F mu nu dual is half A epsilon mu nu alpha beta F A alpha beta. This term has very interesting properties. This term does not change the classical dynamics of Theta to Lagrangian density. This term does not change classical dynamics. What does it mean? It means equations of motion are still the same. Now, if the equations of motion are the same, then this object perhaps is a total divergence, because when you add total divergence to Lagrangian density, equations of motion don't change, right? So this object is a total divergence. L theta is a total divergence. And that's why equations of motion don't see it. Should I leave this as an exercise, or maybe check it? I'll give you the answer. F A mu nu times F dual A mu nu can be written as, now this is what I wrote here, let me write it, is 2 times epsilon mu nu alpha beta F mu nu A F A alpha beta. That's simply rewriting dual in the longhand. This quantity can be rewritten as d mu k mu. That's a total divergence. Where k mu is the following object. A nu A d alpha A beta A plus 2e times 3 epsilon A B C A nu A alpha A beta B C. We are in SU2 gauge theory here, so let me SU2 Young-Mills theory. Otherwise, you would have had corresponding structure constant instead of epsilon. SU2 has epsilon, and general theory we call it FABC. Now, this is an exercise. Just simply take a derivative of this object, various terms, and show that this is exactly same as this. So what does this tell us? This tells us that this object, since it's a total derivative, so this Lagrangian, that we have added this term in Lagrangian as total derivative, equations of motion don't change. So from classical dynamics point of view, this is harmless something. Next, if I were to do the Euclidean theory, see, we were doing this Minkowskian theory. Right? In the Euclidean theory, the corresponding expression for the additional term is the same. If you just go to Euclidean, we learned how to do that, right? Make the analytic continuation to imaginary time, and that will give you an Euclidean theory. Then the corresponding term has the expression exactly like this, but it is an I in front of it. And in the action, there would be a term which is I times S, so which is D for X. But in quantum theory, we know that what is interesting is exponential of the action. So this is the additional term in the action, the full Euclidean action. An additional term is exponential. Exponential of full action has the additional term exponential of I S theta. So this out then tells me is that this, if the quantum theory, this doesn't have to have any effect, then this object, so this object, it's a quantum theory, I'll have this object, but in quantum theory, this object would, if I change theta by 2 pi, would change into I S theta plus let me say, change theta to theta plus 2 pi. So it will give me I S 2 pi. So this object with theta replaced by 2 pi. And this quantity, which is independent of theta, integrated over d for x in Euclidean theory, has integer values. So that means exponential I theta would be 2 pi times an integer. We have not learned that, which is this quantity d for x divided by 16 pi square to 16 pi e square f dual f. Yes, 2 pi I times an integer. I is there, and theta value is 2 pi that I wrote there, and this is so that means 32 pi square, right, as it is. The 2 pi I have taken out here. This object is an integer. This is a 4-dimensional generalization of the topological charge that we consider for Sine-Gordon theory and Sine-Gordon theory, or this is also a 4-dimensional generalization of magnetic charge we consider topological charge. This is another topological charge. So let me not discuss that right now, but let me only tell you is that this object turns out to be an integer. And if it turns out to be an integer, what does that tell me? That there is no change. If I shift theta by 2 pi, this object does not change. That tells me that theta is an angle. With period 0 to 2 pi. Yes, the small l n and the capital N is the same.
What is the thing in front?
E square by 32 pi. So what does this tell us? That and this is exactly what is called instanton number. This is instanton number, and this turns out to be an integer. And if it's an integer, that tells me that if I shift theta by 2 pi, exponential I s theta shifts by 2 pi n, exponential 2 pi n, and that is 1. So which means in this theory, theta going by theta plus 2 pi, you don't change the theory. So which means theta is an angle with period 0 to 2 pi. Right? So till now we just introduced as a parameter. Whether it was an angle with a period, we didn't know. But this argument tells us it's an angle. Now you also realize why I normalized theta by 2 pi in the other case, because I'm going to identify this theta with that theta. All right? Now let's see what does this theta mean. Before that, let me make a few more remarks about the properties of this term. This L theta that we wrote here, we can rewrite in the following way. Rewrite as theta by E square divided by 8 pi square times the non-abelian electric field times non-abelian magnetic field. You know how to write the electric field as the components of F and magnetic field as components of F. So you can rewrite that and you find that this can be written as E times B. From here, it is very obvious that L theta violates parity, violates CP, symmetries. How do I see it? Let me write down here. Under parity, electric field xt changes to minus times electric field minus x t, magnetic field bi xt stays unchanged. This term changes sign. Under charge conjugation, both electric field and magnetic field change sign. X goes to minus x, right? Parity.
So this conserves C.
Right, but there's
It conserves C, it violates P.
also T or
Let's also see how does it go and T. Electric field xt goes to E x minus t, and magnetic field xt goes to minus magnetic field bi x minus t. So it violates space parity, time parity, but not C, but it violates CP. And CPT we have still 15 minutes. This is, like we said, a topological density because it's a total divergence and it is P odd and CP odd. We considered topological densities earlier also, both in Sine-Gordon model as well as in the Georgi-Glasser model, different topological densities. I think he made that remark one of these days. They are also parity odd. So all these topological densities are parity odd. So which means this theta parameter that I have introduced here measures parity odd properties of the theory. And if this theta is going to be that theta, then that theta is a parity odd parameter. And now let's connect the two thetas. Electromagnetic coupling.
It is the electromagnetic coupling?
Yes.
Well, it's called non-abelian gauge theory.
Yes, non-abelian gauge theory with electromagnetic no, sorry, it's non-abelian coupling. This E is non-abelian coupling.
So we call it E and that is called E naught.
Yes. No, sorry. This is not electromagnetic coupling. This is the non-abelian coupling. Yes. So now let me go back to Georgi-Glasser model and add theta, L theta to it. Georgi-Glasser model was action was d4x minus 1/4 of the gauge field strength square plus covariant derivative of a triplet scalar field minus lambda phi square minus a square potential. Now this phi square is a triplet, so it's a vector. This vector is in the internal space notation. The vector arrow that I put is in the internal space. So it's the length of this vector in the group space SU2. And to this I add the term theta E square by 32 pi square F mu nu B F mu nu B dual. Let me call these B's so that this A is a constant. What we are interested in doing is to construct the electric charge operator in this theory. Recall the vacuum of this theory, which is given by the vacuum expression phi square equal to a square, breaks the gauge invariance from SU2 to U1. And this is the U1 that we identified with electromagnetic theory. And what we will construct today, will construct the electric charge operator corresponding to electric charge of this U1 theory. Now, in the broken theory, U1 theory, we have U1 invariance. So, if the corresponding invariance living in SU2 will correspond to those SU2 gauge transformations which leave the vacuum unchanged. Okay? Gauge transformations which leave Higgs vacuum unchanged are those which do not transform phi b. And these are the ones which will correspond to the unbroken U1. The other two generators of the broken U1 will transform phi b. And let's call the generator of such transformations N. B 1, 2, 3 values. So I have chosen a particular vacuum value. Now I don't want that to be changed.
All of it is the same values. Phi 1, phi 2, phi 3.
Now, how can I parameterize such gauge transformations which don't change phi b? The transformation parameter for such theories, such gauge transformations, let me call it lambda A, is simply phi A, well, phi B divided by A. A is the vacuum expectation value. Under such gauge transformations, delta phi A B, how does phi transform under gauge transformations? Epsilon B C D times the parameter of gauge transformation times phi D. That's the transformation of scalar field in adjoint representation. This is the change This is the small change under these gauge transformations of phi in adjoint represent epsilon BD times the gauge transformation parameter, and this we want to be 0 because we want phi naught to be changed. That is true if lambda is precisely that object, because if lambda is phi c by A, gauge transformation parameter is dimensionless, so that is why we divided by A. Phi c phi d, this is 0. Is that clear? So a gauge transformation, all those gauge transformation where the parameter of transformation is phi b itself. Leave phi unchanged. And how does the gauge field transform? This is the gauge field transformation. And that I rewrite 1 by E d mu of phi b by A, and that is minus 1 by A E d mu Is it clear? Under gauge transformations which leave phi a invariant, and those are given by the parameter transformation parameter as phi c by A, the gauge field transforms in this particular way. This is the subset of gauge transformations, a full SU2 gauge transformations, which is the leftover invariance after game symmetry is broken. This is the set of classification transformations which is generate the U1 transformation. Right? Now at large distances, mod phi a square is A. That means this transformation lambda by A, transformation parameter, sorry, lambda which is phi mod divided by A is 1. So if I construct an operator for such transformations, and that's the name I have given it, that a name n, then on the states the transformation would be implemented by an operator exponential of 2 pi I times n. 2 pi is a normalization. The operator on states is a corresponding operator which implements these kinds of gauge transformations on states. And these are the gauge transformations which go to identity at r equal to infinity. The parameter goes to infinity, which means r going to infinity, these gauge transformations have no effect. If they have no effect, that tells me this corresponding operator that I can construct should be such that r going to infinity, it has eigenvalue on physical states and integers. So which means exponential 2 pi I n at r going to infinity should be 1. On states, this as an operator acting on states. So which means at this operator n at r going to infinity should simply implement a rotation by 2 pi. Should be unit 1. So I normalize it. So it should implement simply a rotation by, so I get back to the same point. Which is okay. But for smaller distances, which means r not infinity, this operator will introduce rotations by an angle 2 pi lambda mod by a. A smaller angle, which at r going to infinity will become 2 pi. Mod lambda, that's phi, which is, I should write it as mod phi by a, right? Yes. Now, corresponding to this routine invariance, there is a corresponding Gauss law. And what this tells me is that Gauss law tells me is that all those states on which this object at infinity is 1, this object on physical states will leave the physical states unchanged. Now let's construct this operator n. We just Gauss law is that Gauss law tells you that if this is conserved on physical state infinity, it's conserved everywhere because this is the charge. It's a conserved charge. Now let's construct this n. Construct this n. And conserved charge associated with a symmetry is constructed by Noether prescription. So constructed by, use the Noether prescription. So this n is d3x of, take the variation of L with respect to the time derivative of the fields times the variation with respect to the field. That's what Noether charge is. Take the Lagrangian and take the time derivative, the variation with respect to time derivative of the field, I multiply by the transformation variation. So we have these fields, but we have also scalar fields. This is the standard method of calculating conserved charges by Noether. And here we substitute now the variations with respect to the symmetry that we have. We are interested in constructing the charge for the Noether charge for that symmetry. But that symmetry leaves this unchanged. Those transformations leave this unchanged. So we have only this much as to calculate. And there is a minus sign because that's the gauge transformation is this transformation is this. Yeah, oh, I write B sometimes A sometimes. Is that clear? We have the time derivative of A0. Yeah, AI. So that times that, this the standard Noether trick. If you don't remember it, this is the next exercise, do it. Variation with respect to time derivative of the fields and times the change in the fields under the symmetry. Time derivative of the fields and change in the symmetry. But this is 0 under this particular change in fields that we are doing, and this object is this much. So this is now let's calculate that. Oh, we are running out of time. I'll just do it quickly, 5 minutes. I'm almost at the end of it. We have this term here, 1 by 4 variation with respect to time derivative of A I of f mu nu B f mu nu B. This term. Now this is simply 1 by 4. There are two factors of this kind, so I have another factor of 4 times f b0I. Simple. And this object is E, so I have simply EBI. This minus times this is what we called EB earlier, the electric field. A. And this is minus EBI because metric, we pull it down and change the sign. Then I have this term here. So let me also take 1/4 by delta. I didn't do error again now. and this you can rewrite it as half epsilon I j k f a j k, and that we called minus b b I or plus b I down. So now let me put that in n. 1 by a e d3x of e b I covariant derivative of phi b minus theta e square by 8 pi square b I covariant derivative I this variation gives me from here the first term, and this variation gives me second term from this. These are the only places where derivative of a are time derivative of a are in action. Now you can recognize these objects very clearly. What are these objects? This is 1 by e. This object is q. What is this object? Magnetic charge. So the Noether current for those U1 transformations, Noether charge for those two U1 transformations that we calculated is simply 1 by E, the coupling, the electric charge of the U in the U1 theory, minus theta E square by the magnetic charge. And on physical states, if I take this to be a quantum operator now, because it will act as exponential 2 pi I n on physical states, and we argued that n must have eigenvalues integers. Physical quantum states, n has values n. This operator n, big capital N, curly n, acting on physical states has eigenvalues small n. Put that in, and what do we get? We get n times E is equal to q minus theta E square by 8 pi square G. And let me write this now. G is m times sum G0. And then Q is equal to n times E plus, did I do it right? E squared, that's correct. So then I have n times E, and so if I put m times and this object is m times 4 pi by E naught. So this E, so if I call E as E naught, because that is the minimum charge in this theory, E is the same as E naught. So I have an E naught here, and then this is theta, oh, let me write, is E naught n plus theta m by 2 pi for E equal to E naught. Is this what it is? That's what it should be. Does this give that? Nah. If I replace this G by m times G naught, or replace it by this 4 pi will go away, m is there, so that gives me 2 pi, theta is there, and then this m is there. Yeah, that's it. So this is the same thing that we had earlier, and Q plus IG now is simply so this is the same thing that we had obtained from analyzing the lattice for n0 value equal to 2, but that n0 value is equal, n0 is 2 for the Georgia-Glasser model, because E0 times G0 is E0 times G0 is 4 pi. I have dropped H cross everywhere in this analysis, where in early analysis I had H cross. I divided by E square. This E is the same as E naught, the minimum E naught. Now one last remark. For a pure magnetic monopole, which had that I had earlier, which corresponds to n equal to 0 here, n equal to 0, Q is theta E square by 8 pi square G. Now something funny has happened. As an object which was classically pure magnetic monopole, because of the presence of this theta term that we have here, has picked up an electric charge which is given by theta E square 8 pi square times the magnetic charge. And that's what is called Witten effect. Is that in nature, if theta is non-zero in nature for some reason, then you can never have a purely magnetic charge object in nature. It will have an electric charge which depends on theta. Smallest electric charge which will depend on theta. Right? With that we stop now and think.